now let's go back to what we discussed previous lecture. We discussed about the halfway rectifier, which uses just a single diode. And you notice that using a single diode, the negative half of a sine wave that is supplied by the voltage source, it's suppressed, or it's making, a DC voltage, but, the advantage and disadvantage of this rectifier. You notice that in terms of, the power supply or the amount of voltage as DC type voltage, or the average voltage supplied to the load resistance, or the V out, it's pretty small. It's about 31% or 31 or 0.317 of the peak supplied voltage. Another disadvantage is using just half of the sine wave from the supplied voltage or the signal voltage source. The power is low, or it's much lower that it's supplied to the load resistors. Advantage is very simple. You notice that it uses just a single diode. Now let's see if we can manage to convert actually the negative side of a sine wave of the input voltage into a positive sine wave. And this is what we are looking for. We are looking to convert a full sine wave into a DC voltage. You notice that the pulsating voltage, or the voltage that is at the output of the full wave rectifier, has both halves of the waveforms, means that the average voltage, the average power, is increase, or it's twice of the halfway rectifier. Actually, there are two different ways of making a full wave rectifier. One way is having or using a center tap transformer and just two diodes. Now, we don't know too much about transformers. I just mentioned in the ELE350 when we discussed about inductors, coil, or solenoids. That's another application. We'll discuss in details about the transformer in next course, ELE350, electrical machines. But at this point, I'm just making a very basic introduction into transformers, because we are using a transformer most of the time as the input voltage. Now let's have a look on those diagrams. Firstly, you notice that the three main parts of a transformer. Basically, a transformer has the input, or one of the windings, connected to a voltage source. Another winding is connected to a load resistance. We may have three different cores. One is the air core, the ferrite type core, and the iron core. Now, to make an easy way to look at a transformer, I will stop sharing this file, and I will try to use video if I can do it from here. Could you see me, guys? Perfect. Now, I said that, the basic of a transformer. Suppose that I'm having, those two coils. I make, the two coils, and I put them, side by side. Or in this way, I will make, a transformer. What that means, one of the two winding is connected to a voltage source, and the other winding, for example, the left side or the right side, it's connected to a load or a resistance. Now, to show you a practical transformer. That's, a very small transformer. Probably you can see it. I'm having, the two windings, or those, 3 or 5 or 4 pins of the transformer. That's a very small size transformer. Probably it's 0.2, 0.5 watts transformer. Always, again, relate the size of the transformer with the amount of power, not the voltage, the amount of power that a transformer can handle. Just a larger size, just, a bit larger size. You notice that I'm having a transformer. One coil is placed on top of the other coil and has, the core. Probably on the third one that I will show you to you, we can see actually, the core of the transformer. Probably, I'm having, just a small screen. Let me know if you can have, a good view of, a transformer. You notice that there is a core, and I'm having, the two coils, one on top of each other. But in the same time, we can have, the basic symbol for a transformer that has, the two coils, one on each leg of the core. Basically, what we can do, I mentioned that we may have, the two coils. To increase the magnetic flux or the link between the two coils, I may use, not in this case, I may use a metal core that can handle, the two coils. Now I can bend, this coil to make, a square or rectangular shape of the core, but that's to improve the magnetic flux or the energy that is transferred from one coil to the other coil. Now imagine that, and that's, the easiest way to imagine, the connection between the two coils. One coil is the primary, and the other coil is the secondary. If I'm looking, on any of these transformers, I cannot say, which of the two coils it's the primary, which one is the secondary. Usually you may see a label, let's say, on the body of the transformer, but that's, a very small size transformer, and usually they have, just like a code, like resistors or like diodes. They have, usually a code, printed on the body, on the iron core, or sometimes, is just a sticker on the top. In this way, just by looking at or searching, the code of the transformer, we can determine which of the two windings has, a multiple turns, or has, many turns on primary, many turns on the secondary. The question is, which of the two windings, as I mentioned before, becomes primary, and which of the winding is actually the secondary? There is no rule. I can connect, the one of the coil, let's say, on the right side, on, from your point of view, from what are you seeing, on the right side, I connect, this coil to a voltage source, and that coil becomes the primary winding. The secondary winding, it's the coil, or it's the winding that it's connected to a load. Now I can reverse this process. Yes, I can connect, the left side coil or winding to the voltage source, and the right side winding connected to the voltage source, connected to the load, becomes, the secondary winding. Basically, I mentioned that we have the two windings, the primary winding and the secondary winding. Now let's see if I can start video and go back. Now I'm back to the, let's say if I can see it, from this point. Okay. Now, basically, each of the two windings, you notice that, or the two coils. I mentioned that in electrical machines, instead of saying, it's a coil or it's an inductor, we are saying it's a winding. That's the terminology most of the time that we are using in electrical machines. Again, details about transformers, we'll have probably 4 or 5 lectures in transformers, and we'll see, some other details and some other notes. But I'm looking, just for the basic of a transformer. You notice that I'm having, the left side and the right side of the transformer. I mentioned that if I'm connecting, the right side of the transformer to a load, that winding becomes the secondary winding. On the left side, if I'm connecting, this coil to a voltage source, that winding becomes the primary winding. May I reverse, the two windings? Yes, in some cases I can reverse the two windings. Means that I can connect the right side to a voltage source, and that winding becomes the primary winding. If I'm connecting the left side of transformer to a load, that winding becomes the secondary winding. Always the primary winding is the winding that is connected to a voltage source. Can be, the left side or the right side. Now, we'll make an assumption, at this point, because I'm trying, to simplify, all the observations, and I'm looking, just for the basic of transformers. I'm making the assumption that, the transformer is an ideal electrical machine. It's an AC machine because it does not work in DC circuits. It's usually used in AC applications or in a high frequency DC digital logic, but has to be a variable voltage source that is applied to one of the two windings, which is actually the primary winding. Remember that being an ideal transformer, what a transformer does, it will transfer, that's why it's called a transformer. It will transfer the energy from one coil into the other coil. This type of transformer does not have an electrical connection between the primary winding and the secondary winding. The energy that is created in the primary winding, it's transferred to the secondary winding. Again, look for this any of those three diagrams. I'm having the primary winding and the secondary winding. The electrical or the transformer does not have an electrical connection between the primary winding and the secondary winding. It's transfer. It's actually passed on the secondary winding or to the load through the magnetic field that is created in the primary winding. Now we may see different cores, and in the example that I show you to you, just by placing the two coils side by side, the energy is transferred, but in the same time the core is the air core. Usually I'm just giving some heads up, I'm not asking this point or this course, the applications of the air core, just to give an idea about where we are using the air core. Air core is used in very high frequency applications. I'm talking about kilohertz and megahertz, especially in megahertz or closer to the highest frequency. For the ferrite type core, ferrite type core, it's a mixture, an alloy of iron and some other oxides in it. Means that I can use the ferrite type core in medium to high frequency, like kilohertz, tens or hundreds of, kilohertz. Probably, in this range, I cannot go, above this value because of the saturation of the ferrite core. The iron core, you notice that, the difference between two dash parallel lines, two straight lines, the iron core has, this symbol, means that, the two straight lines or the two solid parallel lines means that it's an iron core. This course, it doesn't matter if the transformer is, the first symbol, the second symbol, or the third symbol, but I'm just giving, some heads up, what is the difference between. The iron core is used for low frequencies. Just to ask, have an idea about, what is the range for a low frequency signal, or what means low frequency in terms of, the hertz, the range of the frequency for a low frequency range. Audio frequency, for example, it's still, a low frequency. Usually the audio frequency is anywhere between 20 hertz and 20 kilohertz. That's, the audio frequency. Usually the iron core, it's used for low frequencies, but the frequency may be anywhere between, few tens, few hundreds. I'm not using, anything, above, these values. I'm still going into practical frequency. The frequency of the voltage supplied in North America is 60 hertz. The rest of the world is it's 50 hertz. That's why, I will bounce, or I will stay, in this range, 50, 60, 100, 200, no more than that. But you may see, some problems, and probably in the assignment you saw a problem that has 120 volts and the frequency is 50 hertz. Now, in order to use, the transformer ratio, I mentioned that always, a useful parameter, or one of the most used parameter, is the ratio of the number of turns in primary winding. You notice that PRI, it's used for the primary winding. SEC, or is the short of the secondary winding. Uppercase N, it's the number of turns, or how many turns of the secondary winding and the primary winding has in it. Now, the ratio of the two windings, the number of turns in primary winding and the number of turns in the secondary winding, can be defined as the turn ratio. Most of the time, the turn ratio has, the symbol of lowercase m. In some other textbooks, you may see the turn ratio as alpha. In some other textbooks, you may see the turn ratio as lowercase a. Both of them, or all three notations may be used, or you may see a different notation. Does not make any difference. It's just a notation expressing or showing the ratio of the number of turns in primary winding and the number of turns in the secondary winding. All the parameters in terms of the voltage or in terms of the current are related to the turn ratio. Again, the turn ratio, n, lowercase n, primary number of turns in primary winding, number of turns in the secondary winding. Down below on the page 8, I put, in writing exactly what means, the uppercase N PRI, the number of turns, or how many turns do we have in the primary winding, the number of turns in the secondary winding. Always, the number of turns in primary winding, it's directly proportional with the voltage applied to it. means that I can make the ratio of the two voltages, the voltage in primary winding over the voltage in secondary winding, as being equal to the number of turns in primary winding over the secondary winding. In the same time, I mentioned that everything is related to the turn ratio of the transformer. In the same time, the ratio between the current, but you notice that it's the secondary current, or the current in the secondary winding over the current in primary winding, is equal to the number of turns in primary winding over the number of turns in the secondary winding. Now, having the two equations, or the last two equations, you notice that I'm having this two equations, voltage in primary winding over the voltage in secondary winding equals the number of turns in primary over the number of turns in secondary. Combining the last two equations, I can simplify that equation, and I'm multiplying the voltage in primary winding with the current in primary winding, and on the secondary winding, I'm having the voltage in secondary winding multiplied by the current in secondary winding. But if I'm looking on this equation, voltage in primary winding is the same, or is equal to the voltage in secondary winding multiplied by the current in secondary winding. Looks like, the power in primary winding, it's equal to the power in secondary winding. And you notice that I made, this statement at the beginning. We are assuming that, the transformer is an ideal machine, which means that the input power always equals with the output power. Now, there are some losses always associated with any of the electrical machines. Now, to put them together, and that's one of the equations that it will be given, the ratio of the primary voltage over the secondary voltage equals with the number of turns in primary winding over the secondary winding, which is equal with the current in secondary winding, pay attention for that, over the current in the primary winding. N is equal to N. Based on this last equation, I mentioned that all the quantities for a transformer in terms of the voltage, in terms of the number of turns, and or in terms of the current is related to the turn ratio. We may have, three different possibilities. If the number of turns in primary winding is greater than the number of turns in secondary winding, or in terms of the voltage in primary winding is higher than the voltage in the secondary winding, which means that the N is less than 1. What that means? That's a step-down transformer when the secondary voltage is less than the primary voltage, or reverse way, the primary voltage is greater than the secondary voltage. Now let's look, that's why I choose, this example first. Most of the time we are using the supply voltage as 120 volts. What we are using, in applications, just few volts, 5 volts, 10 volts, 12 volts, 15, and so on. Means that we are using the transformer to lower the voltage on the secondary of the transformer. Means that N is greater than 1. You notice that N is greater than 1. Means that the secondary voltage is less than the primary voltage, and that's the step-down transformer. Some other applications may use, the step-up transformer. For example, I'm having, a voltage source, a function generator, which has, just few volts, 2, 3, 5, 10 volts, no more than that. Let's say a function generator. And in, our prototype, or, our, circuit, we would like to raise, this voltage to, 50 volts or 100 volts. What can we use? We can use a step-up transformer, which will increase the secondary voltage supplied by a low voltage. Means that always the secondary voltage will be greater, or it's greater than the primary voltage. That's a step-up transformer. And the third case, when the two voltages, the input voltage or the primary voltage, is the same or is equal with the secondary voltage, means that the number of turns in primary winding is the same with the number of turns in the secondary winding, which makes the two currents being equal and the N equals to 1. That's an isolation type transformer when the two voltages are the same. We use, the isolation type transformer in the ELE150, the third lab. If you remember, we use an isolation transformer and an auto transformer on the same device, on the same equipment. But most of the time you will see an isolation type transformer as a safety used, in different application. For example, I use, an isolation transformer in the labs to prevent any electrical shocks, for the students when they are touching, those AC voltages. Now, keep in mind that that's, the equation. We may use a simplified notation of that kind of notation that it's used in the textbook. I use this notation to stay closer to the notation in the textbook. And now we'll go in, make, some examples that shows, the transformer and different turn ratio. Now, in the first example, I'm having a transformer that has 800 turns on the primary winding and the turns ratio of 2:1. Now, the question is, again, how it's expressed, that turn ratio. Usually, the turn ratio is expressed as 1 column X or X column 1. That's, the general rule of applying or using the turn ratio. Actually, what that means, this turn ratio, and again, I'm going back to this equation, the number of turns in primary over the number of turns in secondary. Remember that 4:1, what that means, number of turns in primary means that for 4 turns in primary, I'm having just a single turn in the secondary. That's a 4:1 ratio. Let's reverse this number. Suppose that I'm having a transformer that is 1:4. 1:4 means that for a single turn in primary, I'm having 4 turns in the secondary. The 4:1, that's a step down transformer. For 1:4, it's a step up transformer. Always look for, this turn ratio. 4:1 means that 4 turns in primary and a single turn in the secondary. Means that that's a step down transformer. 1:4, it's a step up transformer. And remember that always, this index may be provided, or at least the number of turns on primary, the number of turns in secondary is provided. Sometimes, both of them are given, but most of the time is given the turn ratio and the input voltage. In this example, suppose that it's given, just the input voltage, 120 volts, and the turn ratio. Now, the question is how we can determine what is the secondary voltage if we know, or if is given the input voltage as 120 volts, but pay attention, it's in RMS. As the primary voltage, the question is, what is the output voltage? The output voltage is the secondary voltage, which is actually the voltage that is supplied to a rectifier. Having, the turn ratio of 4:1 means that the voltage is lower with a ratio of 1:4, which is 0.25. multiplying the input voltage 120 volts with uh, uh, the turn ratio 1/4, which is 0.25, makes the output voltage or the voltage in the secondary winding as 30 volts, but that's the RMS. I'm using the RMS input voltage. The secondary voltage will be in RMS. I mentioned from the beginning of this course. Now I'm using, for DC, I'm using Ohm's law, Watt's law, KVL, KCL, voltage divider rule, current divider rule. For the AC theory, I'm using RMS, I'm using average, I'm using the peak and the peak to peak. Make sure that you review, the two topics from the previous two courses, because I'm using intensively in this part, of the or the first part, of the course. Now, suppose that I'm looking again for the secondary voltage. It's the primary voltage multiplied by the N. Now, from what is coming, this equation, I'm looking back, to the main equation, means that is given the primary voltage, is given the turn ratio, means that I'm looking for the secondary voltage. And the secondary voltage is, the primary voltage multiplied by N. 120 volts RMS multiplied by 0.25, which is 1/4, because it's a step-down transformer, makes the output voltage or the secondary voltage of the transformer as 30 volts RMS. From what is coming that RMS? From the input voltage. Now, suppose that, I'm changing, the ratio of this transformer. And I mentioned that. Suppose that the transformer becomes a step-up transformer. In the first example, you notice that that's a step-down transformer because the secondary voltage is less than the primary voltage. Means that it's a step-down transformer. Means that always, the voltage in secondary, it's less than the input voltage on the primary. Suppose that I'm using a different transformer that has a ratio of 1:3. What is the secondary voltage? You notice that is 1:3. Means that for a single turn in the primary winding, I'm having 3 turns on the secondary winding. That's a step-up transformer, which makes the secondary voltage 3 times higher than 120 volts. Means that it was just 360 volts. Make a change, please, in your notes. I made in my lectures, but I forgot to make the change in D12. Make a change in your notes and make the, instead of 390 is 360. It's actually 3 times 120, which makes 360 volts RMS in the secondary. Again, the input voltage or the RMS can be, or the input voltage can be given in RMS, can be given in peak, in average, or peak to peak. Make sure that you are doing, the conversion, you are finding the secondary voltage, and after that, convert to the peak. Remember that all the quantities for AC theory are related to the peak voltage. Peak, peak to peak, average, and the RMS. Now, the question is, for full wave rectifier, I'm using 2 diodes and a center tap transformer. Now, let's see if I can use actually the tools, and I'm using, the commands, and let's make, some changes in this diagram. Now, you notice that I'm having, the secondary winding, let's say on the right side of this diagram. I'm adding an identical winding on the secondary. Let's see if I can draw it on this diagram. I'm adding an identical winding. Let's try a different color, probably. Let's make it green. Okay. Now, I said that an identical winding, and I want to make, the winding which I'm using the mouse. That's why I'm trying to make sorry. Okay. Now suppose that I'll make, this core just a bit longer. That will be, the symbol for the core. And I'll draw, the other one. What that means, two identical windings on the secondary of the transformer. And I will connect, the two windings together. And this common node, I'll connect that to a ground. That's called a center tap transformer. What that means, two identical windings means that the voltage between the ground and the top side and the ground and the bottom side will have, identical voltages. Now remember that we have an AC voltage source. Now let's try to determine the polarity on the two secondary voltages. Now I'll draw a side probably in a different color like, different color like that. The AC waveform. And I said that that's the positive and that's, the negative. And I'll use, different colors. Let's say this color. For the first half. Again, how we can analyze an AC circuit. As a rule, make an assumption. I'm making the assumption, and I'm starting, in this way. I'm making the assumption that the AC voltage has the positive half or the first half of the sine wave applied to the primary winding. Means that I'll make the assumption that, the positive is on the top and the negative is on the bottom. There is a notation. It's called a dot notation. Probably I may use, a different color to show you, the dot notation. Sorry. Let's say that's, the dot notation. I'll put a dot on this side of the transformer and a dot on this side of the transformer. What that means that if, and we'll discuss in details about, this notation in the electrical machines. What that means, the dot notation, the two voltages are in phase. I'll put, another dot, probably on this side of the winding. Means that always, the two windings are starting in this way or in the same way to make, the winding. Means that the winding on the primary side of the transformer and on the secondary side of the transformer has, the same way of making the turns. In terms of the polarity, means that the polarity on the secondary winding on the top side has the same polarity with the primary winding. I will end up with a positive polarity on the top and a negative polarity on the bottom. For the second winding, I'm doing the same thing. Suppose that's, the dot notation. I'll put it on this side. I'll have the positive on the top, where is the ground, and negative on the bottom. Now, suppose that I'm changed. Try to use, a different color. Let's say I'm using this blue. To make, a negative side means that I'm for the second half of the sine wave on the input voltage or the primary voltage. Positive. I said that voltages are in phase. Negative on the top, makes, the negative on the secondary winding, positive on the other end or the other terminal of the first winding, and in the same way on the second winding, negative on the top and positive on the bottom. You notice that I'm having the two voltages. That's, the voltage negative to positive. Remember the convention, always the voltage is from negative to positive. And I use, the previous color. I think, it was that one to make, the voltage with the opposite polarity. Here you go. Now we have, the two halves of the sine wave, which is actually reflected on the secondary winding with respect to ground. Remember that I use, the and I will try to make, a different color for those windings. Remember that we connect the two windings together, and those two windings are connected to the ground. Means that a simplified diagram, and this is, the easiest way to understand, the polarities on the secondary winding, a simplified diagram of the center tap transformer. Now I'm looking, on this transformer. You notice that, this side of transformer is actually, the first winding. The second half of the transformer, identical windings. Remember that that's, the first step. Two identical windings connected together. And the common connection between the two windings, that's, the common connection between the two windings, which will be connected to the ground. That's a simplified diagram of a centered tap transformer. Remember that the two windings, the first half and the second half of the secondary winding are identical or has the same number of turns. What means in those two voltages? Now I'll make, the voltage in this way or the other way. Means that the secondary voltage, always the voltage across the first winding, it's the same or is equal with the voltage across the secondary winding. Again, what is the assumption? The two windings are identical or has the same number of turns. If the two windings has the same number of turns, the two voltages on the secondary winding will be the same. The secondary voltage, which is the voltage between the two formula, means that from the terminal A, I'll label that, terminal A and terminal B, has the two halves of the two secondary voltages, or I can write, the secondary voltage as the voltage between the terminal A and B. And to find this voltage across a single winding, it's the secondary voltage divided by 2. Or the two voltages, VA to ground and B to ground, is equally the secondary voltage between A and B. Secondary voltage is between A and B, and the secondary voltage divided by 2 is between the ground and point A, or between the ground and point B. And that's, the center tap transformer that we'll start talking about, the basic functionality on how that works on the center tap full wave rectifier. Now, tomorrow we'll go through a center tap transformer full wave rectifier and the other way of having, a full wave rectifier is having a bridge full wave rectifier, which requires, as you can see in this diagram, 4 diodes instead of 2 diodes. There are advantages and disadvantages on, both type of the full wave rectifiers, and the equations and the examples, it will be made tomorrow. Again, tomorrow we'll start, with using the center tap transformer, and we'll discuss the center tap full wave rectifier and the bridge rectifier. Any questions, comments, concerns, guys? If you don't have any questions, I will see you tomorrow at 9:30, and have a nice day.